So let's start with today's lecture, which is a journey to the center of a neutron star. To teach you that a neutron star is not just a liquid drop of neutrons. It's a very interesting object. Now, how are we going to approach this question of what a neutron star is? When a neutron star is formed, its temperature will be about 10 to the power 10 or 10 to the power 11 Kelvin. But please remember, in the process of protons becoming neutrons, an equal number of neutrinos were produced. And these neutrinos escape and carry away the heat very effectively. So the temperature of a neutron star drops from about 10 to the 10 or 10 to the 11 to a modest 10 to the 9 degrees or so very quickly within a week or a few days. And therefore, I am entitled to treat neutron star as the ground state of matter. In other words, it is the lowest energy configuration. And let us ask. First thing is, I expect that in the process of collapse, nuclear equilibrium would have been attained. I mean by that, strong, weak, and electromagnetic forces will adjust the nuclear composition to the most favorable one, which is the lowest free energy configuration. Now, I'm going to regard neutron stars as very cold objects, even though their temperature may be 1 billion degrees. Because hot or cold have no meaning in physics unless you compare it with something else. So I must compare kT with the characteristic energy of the system. I can compare it with the Fermi energy of the system, or I can compare it with the excitation energy of the system. Now you know that nuclei emit gamma. Means that the energy levels inside a nucleus are separated by 1 million electron volts or electron volts. So the characteristic energy scale at nuclear density is 1 million electron volt, which is 10 to the power 10 Kelvin. Remember, 1 electron volt is approximately equivalent to 10 to the power 4 Kelvin. Therefore, a neutron star at a temperature of 100 million degrees or even 1,000 million degrees is a very cold object compared to the characteristic energy. The typical excitation energy is 10 to the 10. The Fermi energy will be 10 to the power 12 Kelvin. So kT is a very small number. Therefore, I am entitled to regard a neutron star as being the lowest. Now let's start from the surface of the neutron star. There is nothing sitting on top of it, therefore the pressure is zero at the surface of a star. So what is the lowest energy configuration at zero pressure? What do I mean by that? What I've given you are a certain number of protons, an equal number of electrons, and also roughly an equal number of neutrons. Now you have to bundle them up to something to create the lowest form of energy. So let's start with the nucleons first. You know from various things that we have discussed and also from your other studies that the nucleus which is most strongly bound is iron 56 nucleus, which is the high binding energy per nucleon. So the sensible thing would be to package neutrons and protons into iron 56 nuclei. And then you attach the electrons to them to form iron 56 atoms. Now, if they are moving around like a liquid or a gas, configuration energy, there is entropy associated with this motion, and you would like to minimize that. The best way to minimize that is to tell the iron atoms to stay put. Now they need not form a periodic lattice, they could be like a glass, amorphous. Then you can ask, which has a lower energy? A crystal lattice has a lower energy than an amorphous configuration. Then you have to ask, should it be a body-centered cubic lattice or a face-centered cubic lattice and questions like that. And I think, if my memory serves me correctly, it's the body-centered cubic lattice of iron 56 atoms, the lowest energy configuration. That still leaves me with the degree of freedom of the electron spins, which could be at random. In other words, this ion could be paramagnet. Obviously, I will lower the energy if the spins find themselves either a parallel or anti-parallel, ferromagnet or anti-ferromagnet. And after many years of study, people came to the conclusion that the ferromagnetic state will lower the spin entropy more than the anti-ferromagnetic state. The other thing to appreciate is that the temperature, even a temperature of about 100 million Kelvin, will be below the melting temperature at those densities. If you look in Kittel's introductory solid-state physics book, the melting temperature of a solid will depend upon the density also. So you have every right to convince yourself that the outer layers of the neutron star will be solid, and that solid will consist of ferromagnetic iron 56 lattice. Okay? This is a safe thing to say. This is at zero pressure, which is the surface that you will see from outside. By the way, we will see neutron stars are endowed with very strong magnetic fields of the order of 10 to the power 12 to 10 to the power 14 Gauss. So these iron atoms will not look like your iron atoms in the laboratory, whose characteristic size is the Bohr radius, either this way or this way or this way. But because the magnetic field exerts force when you try to move perpendicular to it, the motion of the electrons in the magnetic field will also be quantized, and the characteristic radius will be the Larmor radius, EB over MC. How does that compare with the Bohr radius, which is the characteristic size of the electrons in orbit? It turns out that the Larmor radius can be very much smaller than the Bohr radius. Therefore, the hydrogen atom will not look like a nice sphere. The hydrogen atom will look like, or iron atom will look like a needle. Its characteristic size in this dimension will be the Larmor radius. The characteristic size in this direction will be a Bohr radius. Okay, so these are exotic atoms. Give rise to very interesting possibilities. But we are not going to deal with that. If you go deeper, you don't have to go very much deeper. Convince yourself, rather calculate at what depth the pressure that you feel on your head will equal to the pressure you will feel when you go to the center of the earth. In other words, at what depth the gravitational pressure to the pressure at the center of the earth. Okay? Do a simple calculation using Newtonian mechanics. Now, as you go down the surface of the neutron star, the density will dramatically increase, and by the time you reach 10 to the power 4 grams per cubic centimeter, the atomic shells would have melted away from the nuclei, and you will have a complete free electron gas. In a of course, in the laboratory, it's only the valence electrons which form the free electron. The rest are still bound to the nuclei. Here, everything will be ionized. Now, when you reach the density of 10 to the power 7 grams per cubic centimeter, and you don't have to go very deep for that, the electrons will become relativistically degenerate. In other words, the pressure will now be density to the power 4 by 3. Now, around this density, when the Fermi energy of the electrons exceeds 1 million electron volt, remember the Fermi energy is equal to the density to the power 2 by 3. So at some density, the Fermi energy will reach 1 million electron volt. Iron 56 is no longer the most stable nucleus. That is because an electron from the top of the Fermi level, which has an energy of about 1 million electron volt, can combine with a proton to form a neutron and a neutrino. The neutrino, of course, will escape. In other words, the neutronization process will begin. Now, when that begins, Iron 56 will no longer be the most stable nucleus. Instead, it is nickel 62. Then as you go down further a little more, nickel 62 will no longer be the lowest energy nucleus, it will be nickel 64, and so on. So the moral of the story is, as you go down, the inverse beta decay, which is proton plus electron combining to form neutron and a neutrino, will make the nuclei more and more neutron rich. And when you go to this magical density of 4.3 times 10 to the power 11 grams per cubic centimeter, this is the number that I had mentioned in the context of Landau's idea of neutronization of matter, what you will find is exotic nuclei. For example, iron 56, then nickel 62 and nickel 64, then selenium 84, germanium 82, zinc 80, nickel 78, and so on. And all these nuclei have 50 neutrons in them. Then molybdenum, zirconium, strontium, and krypton. Remember, Superman came from krypton, which has 82 neutrons in them. In our periodic table, you know the number of protons is roughly equal to the number of neutrons. So you have A is 118, Z is 82. Another interesting thing about all these nuclei, for those of you who have studied nuclear physics, they have closed nuclear shells. So that tells you that these are the minimum energy nuclei straight away, right? So you will encounter these exotic nuclei as you go down from the surface. That will remain on the top. As you go down, I'm saying you will encounter these nuclei.
Because these parallel nuclei.
Yeah. That iron doesn't disappear. It's just that as I go down, I will meet newer nuclei. Yes, you are absolutely right. So this is the picture of the neutron star. The outer, let's consider a neutron star of the Chandrasekhar limiting mass, because nature seems to make them with that mass. Most models of the neutron star will give me a radius around 10 kilometers, and all of them will agree that the outer 1 kilometer is a solid crust. The outer layers of the crust consist of iron 56 nuclei arranged in a ferromagnetic lattice. And then as you go down, you find the more exotic nuclei that I've already mentioned. Now, an important thing to understand is that if I go down a little further, the nuclei don't like to accept any more neutrons. Therefore, the neutrons drip out of the nucleus. Just as the valence electrons dripped out of the atoms when you brought them to distances comparable to the size of the atoms, and you had free electron gas and metals, now you have a free neutron gas in the lattice. And that's what I've indicated in the bottom. So the lower part of the crust will consist of a crystal lattice of exotic nuclei, such as the ones that I have mentioned here, and sloshing around will be free neutrons. So let's go back to the picture there. So what I will have is at a density of 4.3 times 10 to the 11 grams per cubic centimeter, below that I will encounter an inner, by the way, this is not drawn to scale, really exaggerated. I will encounter the inner crust, which will consist of exotic nuclei with a Fermi liquid of free neutrons. What happens if I go even further in? I will encounter a density of 2.5 times 10 to the power 14 grams per cubic centimeter, which is the density of atomic nuclei. Convince yourself that starting from hydrogen all the way to the end of the periodic table, that the typical density of atomic nuclei of terrestrial matter is 10 to the power 14 grams per cubic centimeter. I say this because very often when you talk of neutron stars, the tendency is to say, no, I don't believe all that. We have never met densities of that order, so how do we know laws of physics are violated with those densities? You and I are made up of matter whose density is 2.5 times 10 to the power 14 grams per cubic centimeter. We float in water only because the distance between the nuclei is so large that the average density is 1. All right? So when you reach the nuclear density, what you would expect is the nuclei to melt. In other words, the distinction between the individual nuclei disappears, and what you have is an assembly of protons and neutrons with an admixture of electrons for charge neutrality. Now, how many protons will you have and how many neutrons will you have below this density of 2.5 times 10 to the 14 grams per cubic centimeter? That's the answer to the question I had asked before the lecture. Namely, why doesn't a neutron star decay back to a proton and electron star? Now, the neutron decays to proton, electron, and an antineutrino. And at the same time, protons combine with electrons to form neutrons and neutrinos. Now, these two chemical reactions must come to chemical equilibrium. In other words, for steady state, the reaction going this way reaction rate must be equal to the reaction rate going this way. That requires that the chemical potential of the neutron, which is the Fermi energy at low temperature, must be equal to the sum of the chemical potential of the protons and the chemical potential of the electrons. At absolute zero, the chemical potential is same as the Fermi energy. So that statement is that the Fermi energy of the neutron must be equal to the Fermi energy of the proton and the Fermi energy of the electrons. Now, if a neutron were to decay back, going back to my question, then the electron must have enough energy to climb to the top of its Fermi sea and sit there because all the states are occupied there. And Fermi energy is several million electron volts. So when a neutron decays, the characteristic energy of the electron will be equal to the rest mass energy of the neutron minus the rest mass energy of the proton. And there is no guarantee that this electron will be able to climb the top of the skyscraper and sit there. That is why a neutron star is stable against beta decay. It is because of the extreme degeneracy of the electrons. Okay? Now, if you work this out, this chemical equilibrium given by the equality of these chemical potentials, convince yourself, please do this, it will take only about 2-3 minutes to do this, convince yourself that you will get roughly 95% neutrons, 5% protons, and an equal number of electrons. So let's draw the picture again. So what we will have above the nuclear density of 2.5 times 10 to the power 14 grams per cubic centimeter is a liquid or a fluid core consisting essentially of neutrons, 3 or 4 or 5% of protons and electrons. Okay? So that's what, at first sight, a neutron star will look like. Now you can ask the question, but what is it going to look like right near the center? Now this question was asked last time, so I will deal with this question in a few minutes. Okay? But this is an overall picture to which we will come back, and various things indicate to us, including constraints on the equation of state deduced from observations, tell us that this picture is essentially correct. All right. Now, how did we arrive at this picture? I seem to be waving and telling this, but is this the way people really arrived at this assertion? No. They actually did the hard work. And since questions were asked last time, let me spend a few minutes dealing with this. How does one calculate an equation of state, which is the relation between pressure and density? Let us start with densities below the neutron drip, namely in the outer crust. The problem of determining equilibrium nucleus at any density is the same as minimizing the total energy per unit volume. What you have is a fixed number of baryons and charge neutrality. So what you have to do is to minimize this energy epsilon, which is the energy per nucleus, M of A and Z, multiplied by the number of those nuclei, plus the energy of the electrons at a density NV of electrons. So it's a sum of nuclear energy and electronic energy. And you have to minimize this. Well, how do you calculate this nuclear energy, the lowest possible nuclear energy? As I said last time, one uses the liquid drop model of the nucleus, which Niels Bohr taught us, and use something like a semi-empirical mass formula. The semi-empirical mass formula writes the nuclear energy as a sum of surface energy, which is proportional to A to the power minus 1 by 3 per nucleon, where A is the atomic mass, and the nuclear Coulomb energy, which is proportional to A to the power plus 2 by 3 and Z over A whole squared per nucleon. The important thing to appreciate is that the surface energy favors larger nuclei, whereas the Coulomb repulsion energy prefers a smaller nuclei. Therefore, it is this competition or this balance which will determine what is the lowest energy configuration of the nucleus. So that's the principle that you use. Now, you have to do this at all densities. Now, how did this subject evolve? The first person to undertake this job was John Wheeler in Princeton University with one of his students, Harrison. And what they did was to regard the atomic number A and the atomic charge Z as a continuous variable. So you can do this using calculus, how this expression will vary as I change A and Z. But then, some years later, in 1961, if I'm not mistaken, Salpeter said, no, you can't regard A and Z as a continuous variable because the nucleus consists of shell structures, just as atom consists of electronic shell structures. Therefore, you must regard A and Z as discrete variables. And so Salpeter did these calculations, improving upon Harrison Wheeler's earlier calculation. Then came along Boehm, Pettit, and Sutherland, and they said, look, you put the nuclei in a lattice, and you have to take into account the lattice energy, because if you take the cohesive energy of metals, it consists of the lattice energy, and it consists of the electronic energy, and it consists of the energy of interaction between the electrons and the nucleus. And the lattice energy is equal to minus 1.82 Z squared E squared divided by A, where A is the interatomic distance, okay? Now, you see, this is very important to have included at some stage or other, because the lattice energy, because it is a minus sign, reduces the repulsive Coulomb energy by about 15%, thereby favoring even larger nuclei. Remember, surface energy favored larger nuclei, Coulomb repulsion favored smaller nuclei. This reduces the effectiveness of Coulomb repulsion, therefore. So this is the way the subject evolved. Equation of state got more and more refined. All this is at density below the neutron drip density. And here, just to convince you, is a plot. What is plotted on the y-axis is the logarithm of the pressure, What is plotted on the x-axis is the logarithm of the density. I'm not going into the details of this. I just want to tell you that various curves with labels correspond to the equations of state calculated by various people. And I just want to convince you that some honest work has been done, which led to the picture that I drew. Okay? It'll take us too far afield to discuss individual equations of state. Now let us go to the equation of state above the neutron drift, namely the lower part of the solid crust. Density between 10 to the power 11 and the nuclear density of 2.5 10 to the power 14 grams per cubic centimeter. Now what is the essential new physics here? There are free neutrons in addition to free electrons. And therefore, Boehm, Hans Bethe, and Pettig improved upon what had been done earlier by taking into account many-body interactions of the neutrons. This is what solid-state physics did for electrons in metals. And out of that came all the interesting physics of solids, namely the optical properties, the electronic properties, magnetic properties, and so on. So Hans Bethe knew all that very well, and therefore he said, let's now deal with the neutrons in a sophisticated fashion. Now what about the liquid interior above the nuclear density? There the problem is very complicated, because you're dealing with densities which are even more than the density of atomic nuclei. In atomic nuclei, it is understood that the mean distance between the particles inside the nucleus is at the minimum of the potential energy curve. Now you're pushing them towards the repulsive potential energy. So there you have to be guided by scattering experiments, heavy, high energy conditions. And one has to solve the many-body Schrodinger equation. One has to take into account not only body forces and body forces. In fact, Professor R. Rajaraman, who used to work here at the Indian Institute of Science, who is now at JNU, he was Hans Bethe's student, and his thesis was on four-body forces in the nuclei. Okay? So here is the equation of state calculated by Harrison and Wheeler at densities above the neutron drift, namely you are inside the liquid interior. And just for comparison, I have shown here the Boehm-Pettig-Pines equation of state. I just want to tell you that there is a difference because Boehm, Bethe, and Pettig included many-body effects, which Harrison and Wheeler did not. So the inclusion of many-body effects you clearly see, and this is a logarithmic plot, right? So this difference is quite significant. What will this difference amount to finally? It will amount to a prediction about the radius of the star, the density profile, and things like that. Okay? Okay. Now let us go to this question that somebody asked last lecture about whether there can be exotic states near the center of the neutron star. What kind of exotic particles I have in mind? Well, pi mesons, K mesons, and other kind of strange particles. And then, of course, quarks. So let us deal with the mesons first. Pi meson, as you know, comes in three varieties: pi plus, pi minus, and pi zero. Its mass is 139.6 million electron volts. They obey Bose-Einstein statistics and not Fermi-Dirac statistics. Please remember that we are talking about the interior where there is beta equilibrium, which means neutron decaying to proton goes at the same rate as proton plus electron combining to form neutrons. Or in other words, the chemical potential of the neutron is equal to the sum of the chemical potential of the protons and electrons. Now imagine what was happening before. The neutron decayed to proton and an electron. In other words, the Fermi energy of the electron minus the Fermi energy of the proton gave you the Fermi energy of the electron population. Now, a new channel opens up. In other words, here is the Fermi, the neutrons, and there is the Fermi energy. At high densities, when the Fermi energy becomes high enough, the neutron, that should be small letter, sorry, the neutron can decay to proton and a pi meson instead of an electron. Remember, pi meson has a mass of 140 million electron volt, and an electron has a mass of only 500 million electron volt. Therefore, this cannot happen normally, but it can happen at sufficiently high density. At what density do you expect this to occur? That depends on the level of sophistication that you bring to your analysis. A simple-minded estimate will tell me that this process is unlikely to occur at a density less than twice the nuclear density, perhaps 3 times the nuclear density. The nuclear density is 2.5 times 10 to the power 14 grams per cubic centimeter. So we are talking about a minimum of 5 times 10 to the power 14 grams per cubic centimeter or more. So whether or not pi mesons will be spontaneously produced depends on whether, as I journey to the center of the neutron star, whether I will encounter a density of 5 or 6 times 10 to the power 14 grams per cubic centimeter. Now similarly, at an even higher density, when the Fermi energy of the neutron becomes even higher, then I can produce K mesons and other strange particles. Now, for K mesons, the rough estimate is that you need at least 3 or 4 times the nuclear density before you can spontaneously produce the K mesons. For the sake of argument, let us assume that such high densities obtain and pi mesons and K mesons are produced in the neutron star, and ask, will it matter? Now, let us remind ourselves that photons, pi mesons, K mesons, gravitons, we haven't found them yet, obey Bose-Einstein statistics because their spin angular momentum is an interval of h cross by 2. No, h cross, which is a question of half, and you know what I mean. Spin of the photon is 1, and yeah. All right, what does the Bose-Einstein distribution function look like? What is shown below is the Fermi-Dirac distribution function which we have used, and that differs from the Bose-Einstein distribution function with a minus sign in the denominator. So the Bose-Einstein distribution function is the probability that a state with energy Ek is occupied is equal to 1 divided by exponential to the power Ek minus mu divided by Kt minus 1, whereas it is plus 1 in the case of Fermi-Dirac distribution. There is another fundamental difference, and that fundamental difference concerns the chemical potential mu. The chemical potential of the Fermi-Dirac distribution is obviously positive. It is the Fermi energy. It is so many electron volts for copper. But the chemical potential of a Bose-Einstein gas is negative. It can at most be 0. And that 0 obtains for 0 mass particles like photons. Remember, in Planck's law, there is no mu. It is e to the power h bar omega by Kt minus 1. But if you have massive Bose-Einstein particle, then the chemical potential has to be negative. And that is the reason why some interesting things happen. The interesting thing that happens is what is called as Bose-Einstein condensation. It should really be called Einstein condensation. Bose had nothing whatsoever to do with it. Let's recall the history. Bose discovers the statistics for photons and sends the paper to Einstein with a letter saying, if you agree that this derivation is valid, can you please translate this to German and have it published in a German? Did. But in the process of reading Bose's paper, he realized that this distribution is far more general than just for photons. And therefore Einstein realized that for all particles with integral multiple of Planck's constant for the spin angular momentum, this statistics will be valid. Not just that. And immediately he realized that the fact that the chemical potential has to be negative implies that at low enough temperature, all these particles will go into the zero momentum or zero energy state. And then, therefore, in his paper, which he wrote subsequent to forwarding Bose's paper, he wrote a second paper, and right there in that paper, he predicted this condensation. So the credit, 100% of the credit should go to Einstein for this, because it is an extraordinary statement to have made right then and there. As you know, in the last 5 or 6 years, there have been 2 Nobel Prizes in physics because they finally found this Bose-Einstein condensation. All right. What is this Bose-Einstein condensation? Let us consider a degenerate Bose gas. That means a Bose gas at absolute zero temperature, like we discussed the degenerate Fermi gas. Its behavior is very different from that of a Fermi gas. The Fermi gas, as we saw at zero temperature, has an enormous amount of zero-point energy. And that zero-point energy came because fermions obeyed Pauli's exclusion principle. 2, 2, 2, you have to pile them up. But since Bose-Einstein particles do not have to obey Pauli's exclusion principle, at low enough temperature, all the particles can be in the E equal to 0 state. Now please remember that this fundamental difference, namely that the total energy of bosons can be 0 at low enough temperature, arises because the Bose gas has a negative chemical potential. Somebody is interested, you ask in the end, and then I will tell you a little more about why this phenomenon occurs. Now, what the Bose-Einstein statistics tells you is that there is a temperature T0. Below the temperature, the number of particles with energy greater than 0 is given by T by T0 to the power 3 by 2. Therefore, by inference, the number of particles with energy E equal to 0 is given by 1 minus T by T0 to the power 3 by 2. Therefore, at T equal to 0, the second term vanishes and all the particles will be in the zero energy and zero momentum state. Please understand that this Bose-Einstein condensation is a condensation in momentum space and not condensation in the real space. When a gas becomes a liquid, it is condensation in real space. It settles down to the bottom of the beaker. Here it settles down to the bottom of the beaker in momentum space and not in real space. Right? And please remember that this temperature T0 will be a function of density. I will show you the expression for T0 in a minute. And therefore, you don't have to wait till T equal to 0 at low enough temperatures. You remember we said at low enough temperatures, when KT becomes smaller than EF, the new statistics takes over. Similarly, when T becomes smaller than T0, which depends on density, Bose statistics will take over, and that's going to put more and more particles in the zero energy, zero momentum states. Now let's get back to pions and kaons. Let's take pions to be specific. They obey Bose-Einstein statistics, and at low temperatures, they will condense into the zero momentum states. What is low temperature? Sorry, this is this T naught of the previous slide. Tc is the critical temperature for Bose condensation, is proportional to density to the power 2 by 3. Same as the density dependence of the Fermi energy. Therefore, you tell me the density, I will tell you what is the critical temperature below which Bose condensation is beginning to set in. And then you'll find that there is a finite number of particles N0 in the ground state. Therefore, at low enough temperature, all the Bose-Einstein particles will be in the zero momentum, and therefore the pressure will vanish, just as Boyle's law of pressure vanishes at T equal to 0. Forget about T equal to 0. The moment you go below temperature Tc, which is the critical temperature, there will be a macroscopic number of particles in the zero momentum state. Therefore, the pressure of this gas will suddenly become much less than before. Or in other words, the equation of state will be soft. Star will become suddenly highly compressible. Okay? Then it becomes a matter of life or death for the star. Therefore, let us go back to our picture of the interior of a neutron star. Let us assume that we do reach densities of the order of 5 times 10 to the power 14 grams per cubic centimeter. Then below that or above that density, we will encounter pi mesons. And if you go to a density of the order of 10 to the power 15 grams per cubic centimeter, you will encounter K mesons. But as the star cools below the critical temperature for Bose-Einstein condensation, the pressure will drop out and the star will collapse and it will become a black hole, regardless of whether it is below the maximum mass of a neutron star or above the maximum mass of a neutron star. Okay? Therefore, now the question is, do we think this is happening? The last word has obviously not been said on any of these things, but if you ask me if I were to bet today, what will I bet? I will say that there are no such things as pion and kaon condensation in neutron star. How do you know? Well, I have a good reason for saying that. When pi mesons and K mesons are produced, a lot of neutrinos are produced. The neutrino luminosity of the star will increase enormously, and therefore the cooling of the neutron star will be dramatic. Now, we will see on Friday's lecture that whenever you look at the site of a supernova explosion, we find a neutron star there, just as Barder and Zwicky had conjectured in 1934. And we see these neutron stars emitting black body X-rays. And I know, therefore, the temperature of this body must be at least 10 million degrees on the surface and higher inside. Now, if these guys are going to cool very fast, how come I go and see a neutron star at the site of an explosion that occurred on the 4th of July, 1054 AD, and its temperature is still 10 million degrees? That tells me neutron stars do not cool that dramatically. Yes, initially they cool when they form, from temperature of the order of 10 to the 11 Kelvin to 10 to the 9 or so. But they don't cool to temperature below black body X-ray temperature, which is 10 million degrees. From Wien's displacement law, I know that when the temperature of a black body is 10 million degrees, the peak of the black body curve will come in X-ray, soft X-ray, right? Therefore, although the last word has not been said, it is unlikely that such high densities of 5 or 10 times the nuclear density is attained in the center of a neutron star. But please treat this as an open question. Now let's try to assume that even higher density is obtained in the center. What do you expect at a higher density? elementary particle physics tells you that when you go to a temperature of the order of 10 to the power 12 Kelvin, such was the temperature when the universe was 1 second old, there is a phase transition that occurs from hadron to quarks. In the case of the early universe, from quark to hadrons. So what is it that we are talking about? We know now, for a long time now, that neutrons and protons are not fundamental particles. They are made up of quarks, which are bound together by gluons. So inside the nucleus, there are quarks and gluons. Now, the fundamental thing about quarks is that if I separate the quarks, the force between them increases and not decreases. Therefore, conversely, if I squeeze quarks together to very short distances or very high energies, they become free. This is what elementary particle physicists call as asymptotic freedom. In other words, when you go to high energy, you're free. It is exactly the opposite of what we would normally think, right? Therefore, the question that underlies this is, if I squeeze the nucleons together to so much, will the quarks deconfine? In other words, will we now suddenly have a soup of quarks and gluons? But now I'm talking right at the center. Now, it may happen, may not happen, and one reason for thinking it may not happen is that again you will encounter very high neutrino luminosity resulting in very rapid cooling of neutron star. Now I'm talking about a lot of neutron stars which are many of years old, still radiating black body X-rays. Okay? Now, people have also speculated, very deep physicists, that if quarks do happen at the center, suddenly there will be a transition such that the entire star is now made up of quarks. These are called strange stars. Now, I've never understood these arguments, and I don't think the arguments are that compelling, although the people who say these things are they are the high priests of the game. But I have a serious problem with these models, and one of them is the following. According to these models of strange stars, as they're called, quark stars, they won't have any crust at all, maybe a very thin crust. Now this contradicts the fact that we have found 2,500 neutron stars functioning as pulsars, as I will talk about on Friday. Now, one of the first things that pulsars tells us is that pulsars are absolutely stable. That means that the magnetic field of the neutron star is anchored solidly to the crust over millions of years. If a neutron star doesn't have a crust, then hydromagnetic instabilities will completely prevent you from having a fixed field configuration for millions of years. And therefore, this very simple experimental fact, the existence of pulsars, argues against stars which will not have a thick crust. Okay? But let us leave it open for the moment. We just don't know. I just react like this when somebody tells me, no, it will happen. It may happen, may not happen. Let's leave it as an open question. And appeal always to experiments to resolve the issues, okay? Now, as I said last time, since I won't have time to go into that now, let me just mention it. Two of the fastest spinning neutron stars that we have discovered have both a period of 1.5 milliseconds, but their magnetic fields are very different. So how come two are spinning at 1.5 milliseconds? So John Friedman and his colleagues conjectured about 30 years ago that this may be happening because you're not able to spin up a star more rapidly than a period of 1.5 milliseconds. What is it that's going to prevent you from spinning it up? Gravitational radiation. Right? Now you agree that if a star is smaller in size for a given mass, I can spin it faster before centrifugal force becomes dominant. So larger the star, larger is the limiting period to which I can spin it up. So Friedman's point, stated in simple language, is that the fact that the limiting period of a neutron star is half a millisecond, and you haven't reached half a millisecond, you have found 2,500 pulsars, but none spinning faster than 1.5 millisecond, suggests that the equation of state of a neutron star may be stiff, such that the radius never becomes smaller than about 10 or 11 kilometers for a mass of 1.4 solar mass. So there are indirect inferences to be drawn concerning whether the equation of state in the interior is stiff or soft. So if the equation of state is not soft, then meson states and quark states are unlikely to occur. Okay? So let's leave it at that at the moment. The last word has not been said, and the last word will be said only by observations. Okay? All right. So here is a summary of what I have said up to now. So let us tentatively admit that in principle, there is a possibility of having a quark gluon plasma or a soup right at the center of a neutron star. Now I change subjects to something even more exotic. But this time very real. And that is the superfluidity of neutron stars. What is superfluid? Well, if you remember, you would have studied it in BSc or MSc, that Kamerlingh Onnes in Leiden in Holland liquefied helium in 1911, if I'm not mistaken. And then when liquid helium was cooled to a temperature of 2.19 Kelvin, it became a superfluid in the sense that its viscosity became zero. Not small, but zero. Similarly, Kamerlingh Onnes cooled mercury, and at a temperature of about 8 degrees Kelvin, it became a superconductor. Its electrical resistance became identically zero. So this is the phenomena of superfluidity and superconductivity. And both have some very intimate relation to this phenomena of Bose-Einstein condensation. Now let us first discuss superconductivity. As I said, superconductivity of mercury was discovered by Kamerlingh Onnes in 1911 itself. The explanation of it was a great puzzle and attention of the great physicists, Heisenberg, Pauli, Landau, Feynman, so many other people. And it was finally solved in 1957 by John Bardeen with Leon Cooper, who was his postdoc, and his student, Bob Schrieffer. Now, finally, when they solved the problem, this is what it was. We normally think of interaction, potential energy between two electrons being repulsive due to Coulomb interaction. But under low enough temperatures, this interaction can be a net positive or net negative or attractive interaction. In other words, two electrons can form a molecule, which are called Cooper pairs, And these molecules now obey Bose-Einstein statistics because there are two electrons. And then there can be super phenomena such as superconductivity. Let's try to understand this a little better. Here I scanned an old transparency of mine because I was too lazy to draw this picture all over again. So I wanted to look at that picture on the right. It's an instantaneous picture of a crystal lattice. The circles are atomic nuclei, and you will notice that at one particular point in the crystal lattice, the atomic nuclei are closer to one another than in the average. Why is this possibility probable? Because please remember that in a crystal lattice, the atoms are not in a fixed position, they are vibrating. They are vibrating about an equilibrium position, but the phase between the vibrations of different nuclei is random. You can Fourier analyze them in terms of lattice vibrations, which are called phonons, but instantaneously I could certainly have a situation where four nuclei are closer together than the average. What I will have in that region of the lattice is therefore a net positive charge. An electron is there, already happened to be there in that region. Then another passing by electron sees a region where there is a net positive charge, and that electron too is attracted to that region. So thereby, two electrons visit that region for a very different reason. And having visited there, they decide, okay, we'll form a net attractive molecule. Stated in more scientific language, which is shown on the left, please remember, such a static distortion is not static, it is time varying. Therefore, when you Fourier analyze it, you get a spectrum of phonons, which are quantized sound waves. I'm sure you've studied these things. And the picture is two electrons mediated by lattice vibrations feel a net attractive force. This is an ever so small attractive force. The net repulsion between the electrons is of the order of electron volts, whereas the net attraction of the electrons due to phonon interaction is of the order of a milli-electron volt, 1,000 times smaller. Okay? Now, are there any two electrons that sort of form bound molecules? No, as is shown in the bottom of the slide. What happens is, please remember that our electrons in metals are degenerate. They obey Fermi-Dirac statistics. All momenta up to the Fermi momentum are occupied, and all momenta are unoccupied. So what Bardeen, Cooper, and Schrieffer said is, take two electrons which are symmetrically opposite on the Fermi sphere. They have equal and opposite momenta. Their spins are oriented in opposite direction, and they form a molecule. Therefore, this Cooper pair, as it is called, need not be small in physical size. Superfluidity and superconductivity are quantum phenomena where the coherence of the wave function can be macroscopic in size. So the Cooper pair, maybe is one electron going over there, one electron going over here, but in Fermi C, there is some coherence to their properties, okay? So it is these pairs which, if you like, sort of Bose condense to put it in a very oversimplified fashion, and the phenomena of superconductivity arises. I'm stressing this because this is perhaps the most successful of all many-body theories till today. Okay? This idea explained every conceivable experimental facts about superconductors. The discovery was made in 1957. Just as the discovery was about to be made, I know this from the horse's mouth, John Bardeen got a phone call from Stockholm saying that he had been awarded the Nobel Prize for the discovery of the transistor. He was very irritated because he didn't want to go, because he knew that they were very close to solving this problem. Incidentally, he got the Nobel Prize for this also, many years later. Now, it is important to appreciate that the existence of the Fermi sea guarantees the formation of these bound Cooper pairs. No matter how weak the interaction is. As long as the net interaction is attractive, these bound pairs will form. Why is superconductivity such a low temperature phenomenon? Because this attractive energy is only of the order of milli-electron volt. 1 electron volt is 10 to the power 4 Kelvin. Therefore, a milli-electron volt is 10 Kelvin. That's why superconductivity occurs only at liquid helium temperatures. But superconductor, please remember, is not just a metal with zero resistance. It is a completely different thermodynamic state. There is a difference between resistance going and something which is a different thermodynamic state. On the left, I have shown an energy level diagram of a normal metal and a superconductor, and there is an energy gap. So there is a phase transition at a critical temperature from a normal metal to a superconductor. That energy gap in a semiconductor between valence and conduction band is of the order of an electron volt. Here it is of the order of a milli-electron volt. Right, fine. Now, what do I do do I have to go there and click something? Thank you. So please appreciate that a superconductor is a diamagnet, whereas a normal metal is a paramagnet. Paramagnet means the spins are oriented at random, but if I apply an external magnetic field, the spins will align, and there will be a net magnetization. Diamagnet means the susceptibility is negative. It will repel a magnetic field. And there it is, an experimental fact of a magnet at the bottom floating above a superconductor inside a beaker of liquid helium. So if you look at the picture on the top, if I have a metal through which a magnetic field threads, and if I cool that metal to the superconducting temperature, once it becomes a superconductor, the magnetic flux is expelled. So this is the fundamental property of superconductors. All right. What is so special about superconductors and also superfluids is that it is a quantum phenomenon. It is a macroscopically quantum phenomenon. In other words, there is a long-range order. Let's consider something we are all familiar with in the second line. Let us consider a perfectly periodic crystal lattice as drawn in solid-state physics books, with a lattice constant small a. Then, as you know, as you would have studied, that the wave function of the electron, psi of kr, is some amplitude uk of r multiplied by e to the power ik dot r. Now, this amplitude has a fundamental symmetry properties. Namely, the amplitude at a position r plus a is the same as the amplitude at r, or n times a. That is a statement of perfect periodicity of the lattice. So there is long-range order, there is coherence of this wave function. Electrical resistance arises in metal because this coherence is destroyed by scattering of impurities and various other things. In a similar way, the wave function of a superfluid or a superconductor is phase coherent. In other words, if the wave function is written in this yellow box in the form psi of r is an amplitude psi, e to the power I theta of r, and theta is the phase of the wave function, then if I know the phase at any point r, then I can uniquely determine the phase at any other point r. So there is long range order. So let us expand theta of r as a Taylor series expansion. You will find that theta of r is theta of r prime. Then if you work it out, then the superfluid velocity times, then you'll find the Taylor series expansion, you'll find a gradient of theta, right? F of r is f of 0, derivative of f, okay, x minus 0 and so on, right? So I've only written the first two terms of the Taylor series expansion. So the important thing to appreciate is that the superfluid velocity is the gradient of the phase of the wave function, okay? The superfluid velocity is the gradient of the phase of the wave function. Remember that. So that's what, all right. Now, I know this from John Bardeen himself, that there was a meeting in Washington, state of Washington in America, where the Bardeen-Cooper-Schrieffer theory was presented for the first time. And there present at that meeting was the great Russian theoretical physicist Bogolyubov. In those days, remember, there wasn't much traffic between Russia and the United States. But Bogolyubov, for some reason, was allowed to travel. So he took back with him a copy of this paper by Bardeen, Cooper, and Schrieffer, and when he went to Moscow, gave it to the Landau gang. There's a bunch of young kids working with Landau in what is today called the Landau Institute. And they immediately applied this theory to neutron stars. A.B. Migdal, one of Landau's students, immediately applied it to the protons in the interior of neutron stars and showed that the protons will become superconductors. 5 years later, Ginzburg and Kirschnitz argued that the neutrons, as well as the neutrons in the interior, will be superfluids by applying Bardeen-Cooper-Schrieffer theory. And please remember that both these predictions were made long before neutron stars were discovered. Because till 1968, when Jocelyn Bell's paper appeared in Nature, neutron stars were discussed seriously only as one chapter in Landau and Lipschitz statistical physics, condensed bodies. So to the rest of the world, they're all forgotten about Chandrasekhar, Oppenheimer, and Volkov. Nobody took it seriously because there was no reason to take them seriously in terms of finding celestial bodies. But Landau's group functioned very differently. They treated it as a piece of theoretical physics, and neutron stars exist, this must also happen. Now at this point, you will see, well, by the way, in 2003, Ginzburg was awarded the Nobel Prize for his contribution to the superconductivity of metals. Now you'll say, but this is nonsense. Superconductivity in metals arises at very low temperatures. Now you're talking of temperatures of 10 to the 8 Kelvin. No problem. Because to have superfluid state, there has to be an attractive interaction between the fermions to form Cooper pairs. Now the strength of the attraction and the density of states at the Fermi level, N of EF, density of states is the number of allowed energy levels in the vicinity of the Fermi energy. That determines the transition temperature. So if you look at the equation of that yellow box, the transition temperature to superconductivity, Tc, is the Fermi temperature Tf multiplied by exponential to the power minus 1 divided by the density of states at the Fermi energy multiplied by the attractive potential energy V. So as V increases, you notice the transition temperature increases. And as the density of states of the Fermi energy increases, the transition temperature will increase. Now, please remember that I don't have to do anything fancy by invoking electron-phonon interactions and all that to create a net attractive interaction, because the net force between two protons and two neutrons is naturally attractive due to the nuclear force. And it is very strongly attractive. Therefore, the transition temperature, Tc, if you now put in the strength of the nuclear potential, attractive potential, remember I drew that picture? Put in the strength of the attractive nuclear potential, say at the minimum, and the density of state of the Fermi energy, appropriate to a density of 10 to the power 14 grams per cubic centimeter, you will get a transition temperature anywhere between 10 to the 9 Kelvin to 10 to the power 10 Kelvin. Compared to that, a temperature of 10 to the 7 degrees or 10 to the 8 degrees is ultra low temperature. Therefore, a neutron star will become superfluid and superconducting if the Bardeen-Kuper theory is correct, and we know it is correct. Okay? So this was the argument of Migdal and Ginzburg and Kirschnitz for why protons will be superconducting, neutrons will be superfluid. What the electrons, will they become superconducting? No, they will not become, because of their low mass. The same old problem, temperature is too high for electrons. They are not too high for the protons because they are 2,000 times heavier. Okay? Remember in our expression for the Fermi energy and everything, the mass of the particle comes in the denominator. All right. So what is it that we have set up to now? Go back to the central portion of the neutron star, which is the bulk of the neutron star with all the amount of inertia there. There's only a thin skin over there. This is not electron superconductor, but proton superconductor. Now let us turn our attention to the neutrons in the lower crust, which are spilled out of the nucleus, and the neutrons in the fluid core. They will become superfluid, like liquid helium becomes a superfluid at 2.19 Kelvin. Now I would like to convince you that both the proton superconductor and neutron superfluid in a neutron star will be rather exotic. Let us first discuss the neutrons. Now, please remember that our bucket is rotating. So let us discuss the problem of a superfluid in a rotating bucket here on this table. Now, the first thing to appreciate is that superflow is a potential flow. In other words, a superflow cannot support circulation. Why it cannot support circulation? Because the curl of the velocity is zero. Circulation is determined by the curl of the vector field. And why is the curl of the velocity zero? I already explained to you that the wave function is of the form modulus of psi e to the power I theta r, and the velocity of the superfluid is the gradient of the phase of the wave function. And the curl of a gradient of a vector is zero. Therefore, a superfluid is not allowed to rotate. If I have a bucket of water, and if I rotate the bucket, slowly the water will start rotating because viscosity which connects the water with the walls of the bucket. But in a superfluid, the viscosity is 0. And circulation is not allowed. But you know, gut feeling, that from a thermodynamic point of view, the free energy will be lowered if the superfluid rotates. So this was a major problem in physics for a long time. And the problem was solved one day by Lars Onsager in 1949, and then it was independently solved by Feynman some years later in 1956. See, Lars Onsager, he wrote only 14 papers in his life, if I'm not mistaken. At least 3 of them, he should have got Nobel Prize. He got 1 Nobel Prize, but he should have actually got 3 Nobel Prizes. Okay, not bad, 3 out of 14. And so his papers were very seldom read. And so it went unnoticed till Feynman. Feynman tried very hard to solve the superconductivity problem, didn't succeed. But he came upon this deep insight. If you read Feynman's biography, written by Jagdish Mehra, you will see that Feynman considers this as one of his greatest discoveries, or something intellectually terribly challenging, even for somebody like Feynman. So let us try to understand how Lars Onsager and then Richard Feynman solved this problem of a superfluid in a rotating bucket which refuses to rotate. Okay. What they said was, this is very irritating. You know, I made these slides yesterday, all these symbols, that's supposed to be a dot product, that's supposed to be... Why does this happen? Is it the version, my version of Windows is different from this? Or it doesn't happen if you don't use Windows. I know that none of my friends use Windows, but I am so dumb that I can only use these things. Anyway, that's meant to be a dot product. Solve this problem. What Onsager and Feynman said was the following. What a superfluid will do is to create a needle. Inside that needle, it will destroy fluidity. So inside that needle, you have normal fluid. And a normal fluid is allowed to rotate. But these are tiny needles of microscopic size. Therefore, when the fluid rotates, just as the angular momentum of an electron in an atom has to be in multiples of Planck's constant, the circulation of this fluid must also be quantized. The quantum of circulation is Planck's constant divided by twice the mass. Why twice the mass? Because these 2 particles combine to form a boson. So that is where the 2 comes from, right? So that is the unit of circulation. So what they said was, let us consider a bucket whose radius is r, rotating with an angular velocity omega. The circulation, which is the cyclic integral of the velocity dot dl, dl is the length in that direction, is 2 pi r multiplied by v, which is omega r, for rigid body rotation. And what Onsager and Feynman said was that this circulation, which is the left-hand side, must be equal to the quantum of circulation, which is h divided by 2m, multiplied by the number of these vortices, which are now called Onsager-Feynman quantized vortices. So these are vortex tubes, which are quantum vortex tubes, each having only 1 quantum of circulation. All right? Now, if I now apply this to a neutron star whose radius is 10 kilometers, so the bucket is 10 kilometers in radius, spinning with a period of 1 second, there will be 10 to the power 51 of these quantized vortices. So the center of a neutron star is not just a superfluid of neutrons, but that super divided by 10 to the power 51 quantized vortex tubes. What does this buy you? Well, Okay, fine. This was also a long time ago. Then in 1971, a paper appeared in Physical Review Letter. An experiment was done in Berkeley and California in a rotating beaker of superfluid helium. As you rotate, a vortex appears. As you rotate more and faster, 2, 3, 4, and then you see they arrange themselves in a beautiful periodic lattice. The number of vortices is proportional to omega. The number of vortices is proportional to the angular velocity of rotation. You see that very clearly. And so when Feynman read this paper, he sent a postcard to that author, and the postcard simply said this: visions in the head at night 20 years ago, coming out in black and white physical reality. Okay? So it's a very poor picture, it's a very difficult experiment to do. But here is a spectacular picture, a recent picture of quantized vortices in a droplet of Bose-Einstein condensate. They cool these atoms using lasers. You've heard of laser cooling of atoms. Cool them to nano-Kelvin temperatures, and then they become a Bose-Einstein condensate, and you spin them using some magnetic field, and there you see quantized vortices appearing and increasing in number as I spin faster and faster, and you see how they arrange themselves into a beautiful periodic lattice, because that will lower the energy. Okay? Here is another picture. We've always been told rotation is analogous to magnetic field, and magnetic field is analogous to rotation, right? Current goes around in a loop, it produces magnetic field. Therefore, you expect something like this to happen in a superconductor also. Okay, first the superfluid. So here is my bucket of superfluid, and it pierces itself with just the right number of vortices corresponding to the angular velocity. And what is plotted below is the velocity v in the vertical axis as a function of the radial distance from the center. If the bucket rotated as a rigid body, then v is omega r, which is a straight line. That is rigid body rotation of the bucket. But what you find, if you really look very closely, is that the velocity field diverges, goes to infinity right at the center of these vortices. But from a distance, from a macroscopic point of view, it will appear to you as though the superfluid is rotating as a rigid body with the right circulation. So right in that paper of 1964, Ginzburg and Kirschnitz mentioned this also, that not only will the neutrons will be in a superfluid state, but it will be in a vortex state. Okay? Now let's turn. Okay, now let us ask the question, is this all of academic interest? I don't think so at all. Because if superfluidity occurs, then it has several very important astrophysical consequences. For example, as we will see on Friday, neutron stars emit radiation. That radiation carries away not only energy but angular momentum. And therefore the neutron star spin slows down. So I have a bucket of superfluid here which is rotating. I put my hand on it and I slow down the bucket. But the superfluid won't slow down. But sooner or later it has to slow down. And there is a time lag. And that time lag causes star quakes in a neutron star. These star quakes are pretty spectacular. They are 56 or 58 on the Richter scale. You remember the most powerful earthquake on Earth is about 8 on the Richter scale. And it's a logarithmic scale. So from 8 to 58. So you can imagine the energy released in a small quake of this neutron star. Now as the neutron star slows down its rotation, the number of vortices has to decrease proportionately to omega. Therefore, these vortices will have to migrate and annihilate themselves on the wall of the bucket in suitable numbers. So it can drag something with it. So some years ago, I came up with a theory of how the migration of these vortices outwards can actually result in expulsion of the magnetic field from a neutron star. Okay, now let's go to that question. It will become more meaningful when we turn our attention to proton superconductivity. Now, while the reason for the onset of proton superconductivity may be compelling, the star is faced with an embarrassing dilemma. Now imagine a neutron star which is born, it is cooling down, at some time it reaches a temperature where it would like to become a superconductor because it is energetically a lower energy state. Superconductor is a diamagnet. It has to expel the magnetic field. This time you are not talking of a few Gauss, you are talking of 10 to the power 12 Gauss. How is the magnetic field produced? All magnetic fields are produced by current loops. So the only way you can expel the magnetic field is by expelling all the electrons. And then you come to your problem. It will cost me enormous electrostatic energy to expel the electrons. So what does the metal do? It wants to become superconducting, but it's stuck with a magnetic field. Understand the question? Till it becomes a diamagnet, it cannot become a superconductor. Well, not all superconductors in the laboratory are perfect diamagnets, okay? Most metals, pure metals, when they become superconductors, they are diamagnets. But alloys also become superconductors. Now almost everything is a superconductor. It's a question of how low temperature you cool it. Now it was a long time ago that alloys do not behave like this. Alloys behave as shown in this picture. What is plotted on the y-axis is the strength of the magnetic field, and what is plotted on the x-axis is the temperature, the transition temperature, Tc. So you see that there are two curves. If you look below the lower critical magnetic field, Bc1, you find that the superconductor is a diamagnet. It has expelled the magnetic field. And at very high temperature or very high magnetic fields, superconductivity is destroyed by the magnetic field, and the magnetic field threads the metal merrily. That is this picture. But in intermediate region, the superconductor allows the magnetic field to thread it, but as quantized flux tubes. Okay? Now, this was first pointed out by another student of Landau by name Abrikosov, and in 1958, he constructed a successful theory of what is called as type 2 superconductor. Now, he had a problem. Landau didn't believe in this. So he refused to allow him to publish this paper. Landau made many mistakes like this, like Einstein. In many cases, they were so opinionated about some issue, but in the case of Landau, he would actually prevent people from publishing the paper. And Landau had this terrible car accident, and then doctors from all over the world went there and operated on him. They saved him. He recovered, but intellectually he never recovered. After that only, Abrikosov had the courage to send the paper for publication. And then he got the Nobel Prize in 2003 for his theory of type 2 superconductor, which actually goes back to 1958. Now, what Abrikosov said was that a type 2 superconductor will allow the magnetic field to go through it, but as quantized flux tubes. What is the quantum of flux? Dimensionally, it is hc by 2e. Why 2e? Because 2 electrons are involved in becoming a superconductor, okay? Like 2 m's were involved in the quantum of circulation. So if you look inside a vortex tube like this, the magnetic flux has a maximum at the center, there is a decay length, and this the superfluid number of superfluid density n goes to 0 in the center. In other words, inside the tube, superconductivity is destroyed, thereby enabling a quantum of flux to go through. Exactly as in the Lars-Onsager-Feynman vortex, superfluidity was destroyed so that that little thing could rotate. Okay? Here is an experiment of such quantized flux tubes in type 2 superconductors. And what you see at the bottom is as I increase the applied magnetic field 1 Tesla, 2 Tesla, 3 Tesla, 5 Tesla, the number of flux tubes increases as it should. The flux is the number of field lines per unit area, but each flux tube is a quantum of flux, so it must increase. And they also form beautiful periodic lattices, and these are called Abrikosov lattices. And today it's a very hot subject. These lattices can undergo phase transition. They can become liquid, glass, crystal, and it's a very hot subject in physics today. Now let's go back to our neutron star and superconductors. Here is our neutron star with an external dipole magnetic field. But the dipole magnetic field previously was due to electrons going around a current loop. But now when it became a superconductor, that magnetism has been transferred to the proton fluid, and what you have is quantized flux tubes. How many flux tubes? The number of flux tubes will be determined by pi r squared b, which is the number of flux lines crossing the equatorial plane, divided by the quantum of flux phi naught, which is hc divided by 2e. So in a neutron star whose magnetic field is 10 to the power 12 Gauss, there will be about 10 to the power 31 Abrikosov quantized flux tubes. So again, there are profound astrophysical consequences of this if it occurs. One of the things that we know about neutron stars is over millions and billions of years, their magnetic field decays by 4 or 5 orders of magnitude. This has been a major problem to understand, because if the interior was a normal fluid, then the magnetic field decay timescale will be determined by ohmic dissipation, like in normal metals. Fields decay because ohmic current results in decay of current loops. Now the ohmic decay timescale, if you look in Griffith's book or Jackson's book, you will find is 10 to the power 13 years, because the ohmic decay timescale depends upon the thickness of the wire and the size of the loop and the electrical conductivity of the wire. These are the three things that determines decay constant. Now if you apply it to a star of the dimension of 10 kilometers, you will get 10 to the power 13 years. In other words, magnetic field cannot decay within the age of the universe. Now if the interior was superconducting, it's even worse, because as Bardeen pointed out a long time ago, the flux expulsion timescale from a superconductor is 10 to the power 23 years. So whether the interior is normal or superconducting, the magnetic field cannot decay spontaneously. So some years ago, as I said, I invoked this fortuitous circumstance. This is the only example we know in nature of the coexistence of superfluidity and superconductivity. We know on Earth superfluids, we know of superconductors, we know of no examples here. So there are, inside this bucket, there are two brands of spaghettis. There are the Feynman vortex spaghettis, then there are the Abrikosov vortex spaghettis. One is parallel to the rotation axis, the other is parallel to the magnetic axis. Now, it turns out that these two spaghettis stick to one another with enormous binding energies. And therefore, as the neutron star slows down and the Feynman vortices migrate outwards, they will drag the other brand of spaghetti with them. So this is one way of, this is the only way anybody has been able to think of how the magnetic field of a neutron star can decay. It decays not despite superconductivity, but because of superconductivity. If magnetic field were not in these quantized spaghettis, drag them out by attaching them. So all I'm trying to say is that these exotic states give rise to astrophysical consequences like star quakes, flux expulsion from the interior, plate tectonics on neutron stars, and all these things may become terribly important when in the context of gravitational waves. You deform the gravitational waves, you have to deform the surface, right? So there it may matter whether the surface is like a nice, smooth eggshell or like a cracked, hard-boiled egg with lots of plates. Okay? So here is a final summary. The outer layer, outer crust is iron 56 lattice. Then, as you come down further, you find neutron-rich exotic nuclei arranged in a lattice, but a lot of neutrons are spilled out of, or dripped out of the nucleus, and there is a sea of neutrons which will be superfluid and which will have Feynman-Onsager vortices in them parallel to the rotation axis. Then if you go to the center, you will find predominantly neutrons which will be in a superfluid state, and some 5% or so of protons which will be in a superconducting state. And these will also be in vortex state. So in the center, you will have the two branches of spaghettis, namely the Feynman vortices and the Abrikosov flexoids. So that's a good point to end our discussion of the interior of a neutron star. Are there any questions? Yes, yeah, I think they didn't give us the microphone. It's here. Can you just pass it around? Yeah, so I'll pass this here so you can, in case there, keep it with you, so pass it after. Yeah, go ahead. No, there one. Yeah.
So for this superfluid in a rotating vessel, what does the surface of the superfluid look like? I mean, does it get deformed like?
Will it have a meniscus? You think about it.
Like water has this paraboloid.
That's what I'm saying. You think about it. Little bit. It's a very interesting question you ask. Whether it'll have a, that's called the meniscus, right? Yeah. Think about it. Huh? Very interesting answer to that. Yeah. You'll have fun thinking about it. That's why. Yeah. Yes. Go back to why water will have a meniscus, and then you'll find the answer to that. When I started teaching long time ago, my teacher said, ancient Chinese saying, you give a man a fish, he will have a good meal. But if you teach him to fish, he will eat well all his life. Okay, so I've tried to live by that motto. Yes, and yes, you had a question.
You said that the iron 56 was in RNA-BCC, right? BCC lattice.
Please remember, these are all things I'm out of touch for longer than before you're born. So it could be BCC, it could be FCC. Go and check which is the correct one. But the point is, people have done the hard calculation and come to the conclusion which is the lowest energy, whether it's ferromagnetic, antiferromagnetic, BCC or FCC. But continue with the question. I could be wrong. See, I don't have access to library and so on. So all these things are straight from my memory. Some of these things could be wrong. They're not wrong intentionally. Okay? Just my memory fails me. But it's a calculable thing, isn't it? It's a question of calculating which is the lowest energy. By the way, that is why these various crystal structures occur for various elements. Because given the number of electrons, different crystal structures are the lowest energy configurations, right? Yeah.
Okay.
Do you have something beyond that?
But like they are assuming they are spheres, right? The atoms are spheres, or like if they. But you said that they may not be spheres.
The atoms are not necessarily spheres. So what that will do is the tensile strength of a lattice will depend upon whether they are like atoms are like ping pong balls or like needles. In other words, whether the forces are scalar or vector or tensorial. Okay? So it will numerically affect all these things, and people have tried to put in all these things into the calculation. Spaghetti-like atoms, needle-like atoms near the surface. Yes, it's very important. Finally, they will determine, when you calculate the total energy, these things will.
Okay.
But I'm sure you appreciate that the nature of the forces per unit volume will depend, right? If they are needles as opposed to spherical bodies. In one case, you will have tensorial forces. Tensorial means what? If elasticity is a tensor, right? If I pull something in one direction, deformation doesn't have to be necessarily in that direction.
I have one more question.
Yeah, please.
How would you know about, how would you find out the age of a neutron star?
You asked me this on Friday.
Okay.
We will discuss that when we discuss real. The cheap answer to that is, in some cases, I know the day on which it was born. If you believe, somebody said long time ago that supernovae occur because of the formation of neutron stars. If that is true, then if you go and look at remains of that supernova explosion, you should find neutron stars, and you do. And because some of these supernovae were recorded by the Chinese and so on, you know when they were born. But even otherwise, there is an approximate way in which deducing. But the basic principle is this: there's a clock which is ticking very regularly. But the clock is slowing down. So people wouldn't appreciate this because you all are products of the digital era. Before, we used to have clocks which you had to wind every day. Grandfather clocks in the house which you wound once a week. And it'll slow down. But from the strength of the slowing down, you can deduce when it was last wound. Okay, so basically neutron stars are not only spinning, but the rate of spinning is decreasing because they are losing energy and angular momentum. So the ratio of the divided by the period derivative of dt. So if I divide the period of a clock by the rate at which the period is lengthening, then I get a characteristic age of the thing. Okay, this is not an exact age, so we can observationally deduce ages of neutron stars, which are, for all, you may be wrong by a small percentage, but it's a very good measure.
Sir, you said it's thermodynamically more favorable for the vortices to form. I didn't get that part. Why is it more favorable, energetically favorable for the quantum vortices to form when you rotate it in a vessel?
Why?
Because you said inside the vortices it's a normal fluid, right?
Yes.
So when it rotates, it should dissipate energy.
When you rotate?
Inside the vortices, it's a normal fluid. And when normal fluid rotates, it should dissipate energy, right? Then how is it more favorable for the vortices?
No, it's the other way around. To destroy superfluidity, I must expend energy. Remember, superfluidity is a lower energy state. So it cost me, so that was the great discovery by Ansager and Feynman. So to do that correctly, you cannot use macroscopic vortices. You have to use these quantized vortices. Read in Feynman, go to Feynman volume 3. He will discuss superfluid. Go and have the pleasure of reading from Feynman himself. Okay? So that was the cleverness of it. That's why they had to be quantized. Instead of, you can otherwise create regions where superfluidity is destroyed and create things, right? That doesn't give you the lowest energy configuration. And that will also not give you the simulation of macroscopic rotation from outside, okay? So that's where the thing was. In fact, that is also a difference between Ansager's solution and Feynman's solution. It's a very good and important question, but go ahead. Let him first.
Sir, you said that like at very high densities, the pion and kaon condensates form, which leads to the equation of state being soft. So, like the matter becomes sort of compressive. So, won't it affect the stability of the star?
Of course, it will affect. It will collapse.
Till when would it collapse?
Look, when you're on a neutron star, you're almost there as a black hole. As I said, a 1 solar mass neutron star has a 10-kilometer radius. The black hole radius is 3 kilometers. So you're dangerously close to instability. And then you put in general relativity and all into it, it'll just collapse to a black hole.
So as soon as the condensate forms, it should collapse.
Sure. Yes. So people invoke this, for example, this supernova of 1886, which the neutrino burst was detected. Nobody has still seen a neutron star there. Now, we don't know how long before a neutron star turns on as a visible object. Okay, we only know the supernova 1054, that was 1,000 years ago. Here, only 30 years ago, exactly 30 years ago, right? The neutron star has not turned on yet. Some people have said maybe because it's a black hole. Maybe because of pion condensation and there was a... So this is the sort of reason why people are thinking about that. Secondly, in a supernova explosion, we assume that the rest of the star is blown apart. But suppose some of the rest of the star falls back on it. Then you will increase the mass. Maybe under such circumstances, the density at the center may go to these densities and they'll form pions and kaons, but in the end collapse. Okay, so the reason why people started thinking about that is a possibility that some supernova explosions will actually produce a black hole and not a neutron star.
I have another question. I didn't get how exactly the flux expulsion in superconductors.
Flux is never expelled in a superconductor, right? It's a neutron star. So because it's only, well, the idea is that as the neutron star slows down, because it's emitting or there is an external brake put on it, the vortices have to go out and disappear in proportionate number, right? And because they are strongly interpinned, it's like a tennis racket. These strings are very strongly coupled with these strings. So if I try to move one set of strings, the other set of strings will also be dragged with it. So the flux can be taken from the interior to the crust. There it can decay due to ohmic dissipation. The crust is not superconducting. That is the idea. Yes, yeah.
So what I was is very in line with what he asked. So I was going to ask that can we have a simplified idea about how this Feynman and Ablyakosov spaghettis are connected? I mean, can you give some simplified idea about that?
This is a very important question, connected with technology also. Why are people trying to try to make high temperature superconductors? Because then you can run trains and things like that by levitation and so on, right? So one of the problems is, and then you can have magnets which produce very strong magnetic fields with a coil being wound with superconductors. So there is no heat energy dissipation there. So one of the problems in all this technologically is this problem of pinning of these vortices. First of all, when you send a current through a wire, it generates magnetic field. And that produces vortices, whether you like it or not. Okay. Now, one fundamental property of vortices is that they pin to inhomogeneities. If you take a vortex, suppose, what I'm saying is, suppose I have a beaker of let's take superfluid, and it's spinning, and let's consider one particular vortex. And that vortex wants to move to the wall of the beaker and annihilate. But at the bottom it's attached to something because there is some impurity and so on. Or in a solid there can be dislocations. So experimentally, the pinning of vortices to inhomogeneities, impurities, dislocations is very common. Now your question is, why do these two brands of spaghettis pin to each other? That is because the spaghetti regards the there are more exotic reasons for it. For example, I said, I didn't say, but maybe I'll say it now. I said in the case of a superconductor, like tin or mercury, you're talking of two electrons on the surface of the Fermi sea, diametrically opposite, equal and opposite momentum, but with opposite spin. So the two neutrons are in 1s0 state. 1s0 state. There is no net angular momentum. But you see, but the neutrons, the core of the neutron star, are at much higher density. At much higher density, the neutrons are feeling a repulsive force due to nuclear interactions. So how do these form bound pairs? They form bound pairs like when helium-3 becomes a superfluid. It became a superfluid a century ago. In 1973, liquid helium-3 also became a superfluid at a temperature of 1 millikelvin. And that's because helium-3 has a net spin. And this helium-3 has a net spin. And there is a strong repulsive energy between these two helium-3. Therefore, they also have a difficulty pairing. And what helium-3 does is that these two helium-3s go around in a sort of an orbital motion so that the net angular momentum is not zero. So they pair 3p2 state. They form in angular momentum equal to one state, p state, and not an s state. So our traditional Bardeen-Cooper refers to S-state superconductor. The net. Before that, people had pointed out in the case of a neutron star, before helium-3 became a superfluid, that if the interior of a neutron star, the neutrons became a superfluid, the only way this repulsive force can be overcome is if there is an orbital angular momentum generated between these two. Therefore, these two neutrons are ferromagnetically aligned. And therefore, the core of the neutron vortex is magnetic with a magnetic field of about 15 Gauss. Extraordinary. What is circulating on neutrons? Neutrons are neutral particles. So this going around cannot produce a magnetic field. But it does produce a magnetic field because of its spin alignment. Okay? So there are many interesting reasons why these two spaghettis stick to each other very strongly. And please remember, they don't just stick in one place. Like in a tennis racket, each string, there are, okay? Remember that 10 to the 31 and 10 to the 50, 10 to the 31 and 10 to the 51. So the number of interpinnings is enormous. It's just that I wrote that, when I wrote that paper, I remember receiving a postcard from Migdal, who was in Princeton at that time, and Ginsberg. Very simple, I treasured them, saying, how come we didn't think of it? So it was a nice feeling to know that. So in a way, they endorsed this idea that it can happen. Any other questions?